Hey, welcome back. So this is the first of a couple sections on a somewhat notorious topic, which is sorting and sorting algorithms. So when I get to this point in my in-person classes, I think this is a topic that a lot of people have been dreading. Some people look forward to it, but it's something that has taken on a bit of weight in the developer, zeitgeist. It's a heavy topic to people, and it's something that is important. And part of the reason, I think, is that it's sort of like the quintessential computer science topic that every blog post ever about getting your dream job at Google, here are 10 things you must master, or every book about acing the computer science interview, there's always a large section devoted to sorting. And for good reason. It is an important topic, it's a great challenge, and it's something that we do all the time, whether we're writing our own code or using a built-in sort method. It's important, but it also doesn't have to be that scary. So let's start by just talking about what sorting is referring to. When we say a sorting algorithm, it's referring to the process of rearranging items in any collection. So we could take a string and sort the individual characters inside a sentence, for example, but we're going to usually be working with arrays, at least for now. Later, we'll talk about sorting other data structures like linked lists or trees, but for now we're focusing on an array. So let's say we have an array of data. We want to write a function that takes that array in and spits out a reordered array. So that could be sorting numbers from smallest to largest, or the other way around, ascending or descending. It could be sorting names alphabetically. Or if we have movie data, let's say movie objects, each movie has a year, a total revenue, it has a director, a title. We could sort them by release year, or we could sort them by revenue. Or we could take their international and domestic revenue, add those together, and then sort by that. So the point is that it doesn't really matter what we're sorting by, what the comparison is, whether it's alphabetically what comes first or numerically what comes first, that doesn't matter. The algorithms behind it don't really care. We're going to focus on working with arrays for now and just numbers. So imagine that I asked you to write a function called sort, and it just takes in an array, and it should return that array sorted. So if I called it like this, with let's just say some random numbers like that, you would need to write code in here in order to make this work so that it should return, let's see, in this case, what are we looking at? 6, 12, 13, 23, and 45 from in ascending order is what we're going to start with. So it's a simple challenge, right? We can look at this. It doesn't seem that bad, but there's a million ways of doing this, and that's part of the problem. Part of what makes sorting algorithms kind of scary is that I can think of 15 probably named algorithms that exist that actually have a name, that are kind of well known, that do the exact same thing. And there are definitely some better ones overall that we will be learning about. Then there are also some that are very niche, that are terrible most of the time, but they do well in certain situations. So just to give you a really quick preview, this is a video I like to show when I'm teaching sorting. We're not going to look at, I'm going to skip around for like 15 seconds, but it visualizes the different approaches to sorting. So basically, over here we have some unsorted data representing, let's say, numbers. The taller items, the taller rows or columns are a larger number. Let's say this is 100, the tallest one here, and the smallest one is representing the number 1. So they're all in this order, totally random, and we write code to go and order them. So here's one approach called selection sort, and you can see that it builds up the array one item at a time. It sorts it one thing at a time until we're done. Then here's another approach. It's called insertion sort, and it's a little bit different. We've got quick sort, very different. We're working from the start and the end at the same time. We've got one called merge sort, another approach, heap sort, radix sort. We're not going to learn every single one of these. There's 15 in this video. Shell sort, bubble sort. But the point is that these are all different approaches. They all end up with the exact same They end up with the same results, but how they get there is very different. So this video is kind of fun to take a look at. I will warn you, the sound is a little bit obnoxious. I'm not playing it here, but definitely don't play it on high volume if you're going to check this video out. So why do we need to learn this? That's the next question. So there are all these different algorithms, and we're going to learn a bunch of them. But why? The first is that sorting is something that is really, really common in programming. And even if you are using the built-in JavaScript sort or the built-in sort method in Ruby or in Python, for example, it still is important to understand what algorithm it's using behind the scenes, because that will help us understand what it's good at and what it's bad at. And that brings us to the next point, which is there are many ways of sorting things, and each algorithm that we see will have pros and cons. So while some are objectively faster than others, there are certain situations where one algorithm, let's say that the data is almost sorted and there's just a couple pieces that are out of place. Some algorithms that are usually slow will be really fast at that. So if you know, for example, that you're working with data that is pretty uniform and it's almost all sorted, but there's a couple things that are out of place, and you want to make sure that it's being sorted as fast as possible, you might want to implement your own sort rather than having to rely on the built-in one, which isn't going to be as fast in that situation. And just to illustrate my point, this is a really cool website I like to show called Sorting Algorithms Animations, and it shows 7 of the most common sorting algorithms: insertion, selection, bubble, shell, merge, heap, and quicksort. These are all different approaches. And what it's showing here are different data sets. So a totally random set of data versus nearly sorted. So you can see we're almost there, but there's a couple items out of place. Totally reversed data, and then data that has few unique items, so a lot of very similar items. Now what I'm going to show you is, first of all, what this does is it just visualizes what happens, just like the video I showed you in the past, but this compares them all at once. So if I hit play on random, you can see how their speeds compare. Whoops, I missed it. There we go. How their speeds compare and their approaches compare. So this is totally random data, and you'll see things like heap, quick, merge, and shell finish much before insertion, selection, and bubble, and poor selection just finished. But then if we look at nearly sorted, you'll see that insertion actually finished. I'm pretty sure it finished first, didn't it? Yep, it's done before anything else. Poor selection, still very slow. And I won't go through all of these, but you can feel free to play around with this. But all that this is showing is that something like insertion, which was slow when our data is totally random, was actually very quick when our data was nearly sorted. I think it was the first one to finish. So they have pros and cons, and it's worth understanding them. And the other reason I didn't put on here that we already hinted at, this is a classic interview topic. It's something that it's a great, it's just a good problem. There's so many approaches. It's really a good critical thinking challenge. I can't believe I'm using that phrase. I sound like my dad. It's a good challenge to do. And it's something that comes up in interviews. So of course, that's a good reason to know something if you're trying to interview. So without further ado, let's talk about what we're covering in this section. Our objectives are, first, we're going to implement bubble sort. So this is one algorithm. We'll learn how it works and implement it. Same thing for selection sort and then insertion sort. So these are what I'm calling the elementary sorting algorithms. They definitely are less commonly used because they're less efficient. But that doesn't mean that you shouldn't learn them. And we'll talk more about why it's important, but I kind of already hinted at it. We saw that at least one of the algorithms performed very well in a certain, very specific situation. So we'll be able to analyze these as we go through and figure out when they perform well. And then after this, we will move on to more advanced sorting algorithms as well. So let's start. First, before we even get to bubble, we're going to talk about the built-in JavaScript sort, the sort method, and just learn how that works. Hey, this video will be super quick. We're just going to talk about the built-in array.sort. So in JavaScript, every array has a built-in way to sort it. Yes, it does. Thank you, slides. But it doesn't always work how you would expect it should. For example, take this array of strings. We sort it, and I think this makes sense. If we get the result that you would probably expect, they're sorted alphabetically. So A for algorithms, then C, then D for data structures, and then steal. That makes sense, I think, to go from A down to Z, or up to Z, whatever. We're going from A to Z. Then if we do the same thing with numbers, 6, 4, 15, and 10, and you sort it, what we get doesn't really make sense. So it starts with 10, and then 15, then 4, then 6. So it would be one thing if it was just the opposite order, like if it was descending instead of ascending, greatest to lowest instead of lowest to highest, but it's not even ordered in any discernible way that we can make sense of, no numeric order. What's actually happening is if we read the array sort documentation on MDN, is that, here we go, the default sort order is according to string Unicode code points. So there's this thing called Unicode used to represent strings, and what happens is that every item in that array is converted to a string, and then the Unicode value of that is taken, and then they're sorted. So it's very bizarre, and it's almost never what you want, unless you're working with strings to start, but even then, it's not always what you want. So how does it actually work? How do we use it in the real world? That's only what happens, that's the behavior when you don't pass anything in. You just do .sort with empty parens. But there's this whole other thing we can do where we can actually specify how it should sort, what property it should sort by, what to compare. So it accepts an optional comparator function, and we can use this to tell JavaScript how we want it to sort. So basically, the structure that we write this function is, it takes two items, which we'll call A and B, and we tell JavaScript the sort order to make based off of what we return. So if we return a negative number, so if we have two elements, again, A and B, JavaScript's going to call this function every time it's comparing two elements. If this function returns a negative number, then JavaScript will decide that A comes before B. If it returns a positive number, then it's the other way around. A comes after B. And if we return 0, JavaScript treats A and B as the same and just sorts them basically together. It doesn't matter. So here's an example. Number compare is what we called our comparator function. And all we're doing is returning num1 minus num2. So JavaScript gets this. Remember, this is what comes first, this is what comes second. If this returns a negative value, then num1 comes first before num2. If it returns a positive value, then num2 comes first and then num1. So when we do this, you can see that it's now sorting things appropriately in ascending numeric order. So we get 4 and then 6 and then 10 and then 15. And I have it over in a snippet here. So if I run it, it's a little big. There we go. So if I run this now, you'll see that we get 4, 6, 10, 15. But if I just change this order, so num2 minus num1, for example, we get 15, 10, 6, and 4. So that's sorting just by numbers, which that's what you would do if you're trying to sort something numerically rather than working, the Unicode characters and worrying about all of that. We could also do something like this to sort by the length of a string. Rather than alphabetically, we want to sort from whatever the shortest string is, so colt, up until the longest string, which would be data structures. So we do the same thing, string1.length minus string2.length. And we call this compare by len, but remember, it doesn't matter what we call this, it's just a random function. But it needs to accept these two arguments, and then we use them in here, and we return a negative number, a positive number, or 0. So what do we get? There we go. And if we swapped it around, change the order, string2.length minus string1.length, now we have the other order. So this is how we can define our own basic sorts using the built-in JavaScript sort method. Now I just showed that to you so that you know that it exists and it's an option. Now what we'll focus on in the rest of this section is writing our own sorting algorithms that actually do the comparisons. That's the hard part. And so that's coming up next. We're going to kick it off with a fan favorite. It's not a fan favorite, but it has a fun name, bubble sort. See you in the next video. Hey, welcome back. So the first of the sorting algorithms that we're going to take a look at is called bubble sort. So bubble sort is not all that efficient. It's not that commonly used. There is one use case we'll discuss where it does excel, but generally we're not learning it because it's going to be, it's not going to rock your world. You're not going to be implementing it all the time. Although it is a very good problem. It's a fun one if you know how to do it, and there's some optimizations we can make. So it's a good thing to talk about, and it also helps us understand why other algorithms improve upon it. So don't skip it, please. Okay, now that I've made it sound terrible, let's talk about why it's called bubble sort. So the idea is that if we have an array and we're sorting from smallest to greatest, so in ascending numeric order, the larger values will bubble to the top one at a time. So what I'm going to introduce now is something that we haven't seen up until now, I think. It's called visual, well, I actually don't know how, I use this all the time in my classes. Visual algo. It's a combination of visual and algo for algorithm. So I like visual go, but the way it's highlighted, it makes me question my pronunciation. So what it is a really cool interactive tool in the browser that lets you step through sorting algorithms, among other things. I'm currently looking at bubble sort. And you can see that we have some data. If you open this up, by the way, your data set will look different. I I input these numbers specifically. I didn't want to have a massive data set that took me like 10 minutes to step through. So we have 1, 2, 3, 4, 5, 6, 7 elements ranging from 10 up to 37. Okay, so this is our array. This is the first item and this is the last item. The way that bubble sort works is that as we loop through each item, we compare it to the next item, the one in front of it. And we check, is this one larger than what we're comparing it to? And if it is, we swap. So swapping is really important to bubble sorts, how it works. You basically swap if something is larger and then you compare it to the next one. Is it larger? Swap again. Compare it to the next one. So let's just step through that. So 29 and 10, we swap because 29 is larger. 29 and 14, that's the next comparison. We swap. Now we compare 29 and 30. This time, we don't swap. So now we have 30 and 37. 30 is not larger than 37, so once again, we don't swap. Now we compare 37 and 14, and now we do swap. Now we're on to 37 and 18. Compare the two, and we swap. So that was our first pass all the way through the array. And what happened is that the largest value bubbled to the top. I've also heard this as sinking sort, where the largest values sink to the end, to the bottom. I think that's a little more pessimistic. Bubble, it's so much happier. Who doesn't like bubbles? So now we repeat the process. I won't make you watch every single step of this, but we start again at the beginning. So we compare 10 and 14. We don't swap. We compare 14 and 29. Again, we don't swap. We compare 29 and 30. We don't swap. Now, we compare 30 and 14, and we do. Next, we compare 30 and 18. Once again, we swap. So now we have the last two values cemented in place, right? 30 and 37, those are sorted. So we're building this list as the values bubble up to the top or to the end, the largest values. We know that those last two items are now sorted. Those don't need to change. And on we go very quickly. We go through this, we swap, 29 bubbles to the top, and eventually we end up with this sorted array. So on the slides, I have a simple walkthrough of one of those iterations. So if this is our array, we swap. If we compare 5 and 3, we swap. So 5 moves up. Next, we compare 5 and 4. We swap again. Next, 5 and 1. We swap again. And finally, we compare 5 and 2, and we swap because 5 is the largest element in the array, and it ends up at the end. So that's for one single iteration. Then all we need to do is repeat that over and over. And you could start by repeating once for every item in the array, but remember that as we go through, the amount of items we need to sort decreases because we started out with 5 elements that were unsorted. Now we have 4 unsorted elements and 1 solidified sorted element. So that means that we have fewer elements to sort as we go through. So our loops can reflect that. But first, let's talk about swapping. Since that's such a crucial part, we have to swap. How does that work? Well, in JavaScript, there's a couple ways of swapping. I have two listed here. This is honestly my preference. It's not the newer way of doing it, but this is how the tried and true way of swapping values. I think it's kind of more legible, easier to understand. You don't even have to make a separate function to do this, of course. But here, what we have is an array and then the 2 indices that we want to swap. And we set up a temp variable to store one of them. And then, so if that's the first one, index of 1, we set up a temp variable and save that to that value. Then we change what was in array of index 1 to now be what's in array of index 2. And then lastly, we use that temp variable to update array of index 2. So that's how I like to do it. But there's also in ES 2015 this syntax for doing it, which I don't know. I just don't think it's very readable personally. But the syntax basically is take whatever's in index 1 and swap it with index 2. Take what's in index 2, swap it with index 1. And this works. And it is a single line. So for those of you who are file size queens, who care about how short your files are, you can use this. I'll probably use both. But it helps to define a function called swap because then our bubble sort code becomes even shorter. The actual logic really is just about the comparisons in the loops, and then we can just call swap. But you don't have to define a separate function. If you want to implement it, which I highly recommend you give it a shot, here are some of the steps. Start looping. So define a function, I didn't add that in, called bubble sort. It takes an array, and you can assume it's all numbers. Start looping with a variable called I at the end of the array towards the beginning. And we'll discuss exactly why, but it has to do with the fact that we're shrinking down the amount of space that we're sorting. Then an inner loop inside of that outer loop with a variable called j from the beginning until I minus 1. So I is referring to the first loop. So we have a nested loop that is depending on the first loop, I minus 1. And then we just compare array of j, so that's going to be our individual. If I went back here, let's say we're comparing, if j is 0, we're going to compare it to array of j plus 1, which is the next item. So whatever j is, we're going to compare the item ahead of it. So j and j plus 1. Okay? So if array j is greater than array of j plus 1, that means you need to swap. And you can swap however you'd like using whichever version that I showed you. And then at the end, just return the sorted array after the loops are done. So give it a shot if you'd like. And in the next video, we'll have an implementation. All right, let's do this. Let's get implementing bubble sort. So I had pretty specific instructions here. Start looping. Oh, I just realized this is a bit of a typo. Sorry about that. Start looping from the end of the array towards the beginning with a variable called I. What I'm actually going to do is show you the dumber, I shouldn't say dumb, the less optimized version that doesn't follow these instructions, which just uses two nested loops that go from the beginning to the end of the array, the entire way. So that would look something like this. I'll define my function. I'll call it bubble sort. I made a new snippet, by the way. It accepts an array. And we know at the end it's going to return that array. And let's say I'm going to call it with a super simple array like 37, 45. I have such a tendency to pick odd numbers like this. It's not on purpose. Okay, we'll put 8 in there. Okay, so this is what we start with. And we're going to loop over every item in the array. So for var I equals 0. And I'm going to do, like I said, just starting from the beginning. So 0 up until, or less than array.length, I plus plus. So that's going to give us a single pass, right? If this is only going to loop, 4 times. So we'll start with I at 0 and it ends at I at 3. So that gets us enough to sort one item. So we could compare and do our swaps. And at the end of this loop, if we did swap things, we would have 45 at the end of the array. But we still have to sort everything else. So we need to repeat that process for every item. Technically, remember, we don't have to do it for every single item every time in that array because as we progress, the end becomes sorted. So if we started with this, the next time through, we would end up with 45 at the end. So then next time, we only need to sort these 3. And if we did that, we end up with 37 bubbling here. And now we only need to sort these 2. But for our naive solution, let's just have the code go all the way to the end every single time. So for that, we just need another loop. So for, call it j equals 0, while j is less than array.length, j plus plus. And now we have j, so j is going to be 0 starting at the beginning, and we want to compare whatever item we're looking at with j to the one in front of it. So j and j plus 1. So that just looks like this. Array of j, comma, array, well, no comma, ignore that. We want to check if it's greater. So if array of j is greater than the one in front of it, swap. So let's write that logic now. Now, as far as swapping, I'm going to start with the basic swap, the tried and true swap, where we make a value, so a variable, I'll call it temp, and set it to one of them. It doesn't matter. I'll set it to array of j. And then we change the value of array of j to be array of j plus 1. Thankfully, we saved the old version in our temp variable. So now we set array of j plus 1 equal to temp. Okay? And that's actually it. This is a working version of bubble sort, but it's just not optimized because of what we talked about. It keeps running over and over. And there's actually another small problem. Let's start by printing out up here, console.log, what the array looks like as we go. All right, let's see if it works. Here's our first pass. We had 37, 45, 29, and 8. We compared the two, 37 and 45. We don't swap. Now we move on. J is incremented by 1. So we compare 45 and 29. And we do swap. You can see that change reflected the next time through. Then we compare 45 and 8, and once again we swap. And so that's what happens here. 8 and 45, that looks good. We have 45 at the end. But here's the problem. And actually, I've changed my mind a little bit. I think what will even be clearer is if rather than just printing the array, console.log array, if we also print what we're comparing. So I'm going to do array of j and array of j plus 1. So we can see the comparison as it happens. Let me clear my console here. Run it again. Okay, so now you can see we're comparing 37, 45, 45, 29, 45, and 8. But then 45 and undefined. So what happens is that we went too far. J hit the end of this loop at 45. Well, j is equal to 3, index of 3, and we're comparing it to index of 4, which there isn't. So we're comparing 45 and undefined. Now our sort still works, but we're going too long. We don't need to do this. Not to mention the fact that now we know 45 is sorted. So we start over. We compare these two, 37 and 29. That is a swap, right? So we do swap them. Then we have 37 and 8. We swap again. And we should be done with this iteration. We should start over and start sorting this. But instead, we compare 37 and 45. But we know that that's already sorted. 45 isn't moving. Nothing is going to be higher than 45 because of the way bubble sort works. It is cemented in place the first time through. So we have a needless comparison. And once again, next time through, you'll see we do the same thing, 37 and 45. There's no reason. So what we want to do is basically at the beginning, we want to make 3 comparisons. So there's 4 items in this array. We want to have 3 comparisons, 1, 2, 1, 2, 3. And then we should start over and next time only make 2 comparisons. This comparison right here, 37 and 29, and then 37 and 8. And then next time through, we should make 1 comparison. Does that make sense? We want to shrink the number of comparisons we're making because we're sorting the array as we go. So the solution to that, if we come and make a couple edits, the first is that I'm actually going to change the way this loop is set up. I'm now going to follow the pseudocode I set up. We're going to start with a variable I that goes from the end of the array towards the beginning. So that looks like this. Set I to be array.length. And we go while I is greater than 0. I minus minus. The reason we do this is so that we can use I in the definition of the loop for j. So j now runs while less than I dot, or I minus 1. What am I saying? Dot. I minus 1. Okay, so at the very beginning, our array length is 4. Well, it's always 4, but I starts at 4. So then this loop, the inner loop, we're going to compare j is less than 4 minus 1. So 3 comparisons. This gives us 3 comparisons the first time through. Because I is 4, that means j goes 4 minus 1, 3. Next time through, I has gone down, I minus minus. So we end up with I equal to 3. So then we have j less than 3 minus 1. So that means 2. This loop will run while j is less than 2. So as I goes down, so does j. So we end up running the loop fewer times each time through. So if I save this, get rid of that extra x, rerun it. Let me clear the console now. Now let's look at the comparisons that are made. So we do 37 and 45. That makes sense. Then 45 and 29. And then our final comparison on this first time through, 45 and 8. And we end up with the first time through 45 is at the end. Then we start over. We're no longer sorting undefined and 45 because of this minus 1. So then, next time through, we do 2 comparisons, 37 and 29, so we swap, and then 37 and 8, and we do swap again. And at that point, these 2 are cemented. So next time through, we only have to do 1 more comparison. And you can see that, 8, 29, we swap them, and we're done. So what I could do, let's change this to be 8, 12, 88, 100. No, let's do -3. There we go, negative value. And if we run it now, let's clear the console first. There we go. Let me actually, sorry, this is annoying, but let me make this easier to see. So after that loop finishes, let's do console.log 1 pass complete, like this. Okay, rerun this. Okay, So now you can see really what happened. The first time through, we did 1, 2, 3, 4, 5, 6 comparisons. Then that was one full pass. Next time through, we did 1, 2, 3, 4, 5 comparisons, and then 4 comparisons, and then 3, then 2, and then 1. So this is one version of the solution. Get rid of the console.logs. I also have the ES 2015 version where I decided to, first I used the old version, the new way of swapping things, and I decided to make it into a function. You definitely don't have to do that. I mean, this is only 3 lines, honestly. But if you wanted to, here is the nicer, some people would consider this solution nicer. I used let as well. And otherwise, what else? Big arrow function. Everything is pretty straightforward though. You just, let's run it and make sure it still works, of course. There we go. -3 up to 88. Okay, so these are 2 working solutions to bubble sort. Hey, welcome back. So we're actually still talking about bubble sort because there's one important optimization we haven't discussed. So there's a very specific scenario where if our data is almost sorted, or if it's already sorted, it doesn't need to be bubble sorted, our bubble sort algorithm as it stands doesn't really treat it any differently. It still tries to sort every single item. So in this scenario where we're almost sorted, if I fast forward through this, okay, maybe this was a bit too long. Okay, we're almost there. Now we're sorted, right? So we get to the end, and as humans, we can see that we're done, but our code is actually going to keep going, and it's going to go to the end. No swaps are made, but then it goes again, and it tries to sort all of these up until here. Then it goes again, tries to sort all of these to here, even though nothing is happening. It's just iterating over. So if we have a super long array, that's going to be a problem because it just takes up a lot of unnecessary time. So we can short circuit our code. All that we have to do is check. Last time through, did we make any swaps? If the answer is no, if we didn't swap anything, that means that we're done. Because if you didn't swap on the last time, you're not going to swap on the next time. So back in our code, what I'll do, I guess I'll make 2 versions. We're getting a lot of solutions going. If we, I guess I'll comment these out for now. I never know what the best way of doing this is because students like to have this different steps as I go, but I also don't like making these super long files because it can scare some people. But what we can do, if we call this right now with a nearly sorted array, like 8, 1, 2, 3, 4, 5, 6, 7, for example. So we're almost there, right? After the first pass, it's going to be sorted. 8 will be to the end. If we take a look right now, how many comparisons we're making roughly, let's run it now. We're making a ton because it was sorted at this point and we kept going without making any swaps a ton of times after that. So what I'll do is I'm going to make a variable. I'll call it no swaps. And no swaps is, if it's true, that means there were no swaps and we're going to break out of the loop. So I could start with that down here, even though it's not defined. I could write if no swaps break. So that would get us out. Of course, we don't have no swaps defined. So up here, I'll do var no swaps like this. And then inside the loop, each time through, I'm going to set it to be true. We'll assume there's no swaps every time through. But then if we make a swap, which is right here, remember, we can set it to be no swaps equals false. Does that make sense? So as we go through, every time at the beginning, so let's say we start with this, no swaps starts at true. And then we make a swap right off the bat. 8 and 1, we swap. So now there's no chance of breaking out this time through. But then we finish the iteration and 8 is now at the end. You could see like here, for example. Next time through, no swaps is true. And we never make a swap. This is never true. So we never set it to false, which means we get through all the way to the end one time afterwards. So we sort it all, then we iterate through no swap, no swap, no swap. Then we get done with it. And this is true now, if no swaps, and we break out. So now if we take a look at how many times this prints out with this line, you can see that we basically had to get it to the end, which was right here. This was our first time through. And then we went through one more time and we finished. And then that was it. We didn't keep going. And compare that to the previous versions where we went through, we got 8 to the end, and then we kept sorting over and over and over and over and over, many more passes. In this case, we shortened it significantly. And as the array grows, if it is nearly sorted, that makes a very big difference. Okay, so I just added a little comment. This is our next version that we optimized with the no swaps variable. Just a small change, but it really can save a lot of time. What is the time complexity of bubble sort? Well, in general, it's n squared because we have a nested loop and we're roughly making a comparison for each item in that array. We are making n number of comparisons. In order to get 8 to the end, we had to compare 8 to every single other item in the array. However, if the data is nearly sorted or already sorted, then with this new version with no swaps, it's more like linear time. That's the best case possible, O of n. There's 8 items we go through. I mean, technically in our example, it was 2n because we went through the first time and then we went through again to make sure nothing was swapped and then we broke out of the loop. So, but that rounds down, or I shouldn't say round, that simplifies down to O of n. So that's the best case, but that doesn't mean that we should be using bubble sort unless you do know that your data is very nearly sorted. It's a good candidate, possibly. We'll also see another good candidate in a little bit. This is more just to show an optimization. This is a classic optimization to make. And yeah, I think we'll end this video here. So we have this version, which doesn't use the fancy swap syntax. Then we have this version that does, using let as well. It's the ES 2015 syntax. And then down here, we have a version where I added the no swaps variable in to short circuit if we don't make any swaps. That is bubble sort. It's a lot, I know. Now we have another sorting algorithm coming up next.